This is Mr. Craig, and I want to go over some issues dealing with bonding. I know that a lot of students have had some concerns, issues dealing with Lewis structures, the type of hybridization, what type of solid it is, all those things. I have placed a copy of this document online, so you can copy this out if you'd like. I do have some examples at the end. I'll probably make another video for the examples since the explanation may take a little while. Alright, the first thing that we need to do when drawing Lewis structures to determine quite a few things about the compound is that the first thing that we need to do is draw a correct Lewis structure. First thing we want is the correct number of valence electrons within the molecule or compound. The way that we do that is we get our periodic table, take a look at what group the element's in, count that as our valence, get a total number there. Next thing that we want to do is determine which atom will be the central atom. A couple things to remember: that if you have carbon, carbon always goes in the middle of a molecule or a compound. Hydrogen never goes in the middle. Once you know who your central atom is, arrange the other atoms around the central atom, and then we want to place the electrons on the external atoms first, keeping in mind the formal charges. Now, we do want our external atoms to have 8 electrons. We have to remember that. Now, also do recall that boron, when it is typically a central atom, may only have 6 electrons, and hydrogen can only be an external atom, and it will only have 2 electrons. But everybody else has to have at least 8. Also remember that when we're talking about formal charges, that if you're looking at an element, say in group 5A, as an external atom, that element wants to have a triple bond. And we'll do some formal charge calculations in the examples later on. If it's an element out of group 6A, the one that has oxygen at the beginning, those elements as external elements want to have a double bond for a formal charge of 0. And then if we're looking at an element in group 7A, it wants to have a single bond. Now you may say to yourself, well, what about those elements that are in group 4A? Well, there is no such thing as a quadruple bond, and the only element that we really care about in group 4A is carbon, and carbon goes in the middle. So we never have to worry about accidentally giving something a quadruple bond, and if you find yourself doing that, stop, because you're probably looking at an ionic compound. Alright, the next thing, once we have our Lewis structure drawn out, we want to take a look at the Vesper shape. Now, you all got a copy of this back in the notes, and if you lost that, then you can get another copy online. I want you to notice that I actually have 2 extra boxes on here. These are not the shapes that you need to know for AP Chemistry. I do know that some universities and colleges around the state here, for the octahedral shape, or where your potential is 6, do require you to know the T-shaped planar and the linear. However, we don't care about that shape, so ignore it for now. However, be sure that you do know this chart and what it represents. And what I have highlighted up on top here, and I had you highlighted in your notes, is potential. And again, this is a term that I use and that no other textbook talks about this, but it is a great system or a great method for being able to name the Vesper shape and for hybridization. So when we talk about what potential is, we want to talk about the number of external atoms plus the number of lone pairs on the central atom only. We don't care about lone pairs on any other atom other than the central. So once you know what your potential is, then you're going to work out of each respective column. So if we say that we have 2 external atoms plus 2 lone pairs, then we're going to work right out of column 4. Okay? And whatever the name will be for this Vesper shape will be one of these 3 for column 4. Then you'll use the information over here in this table over here, or I'm sorry, in the column on the left, to help you determine what the name is. And again, I'll do an example of that here in the next video. Once we know what the Vesper shape is and we know what our potential is, then we can determine the type of hybridization or the type of hybrid orbitals that this element has. And the good news is there's only 5 types of hybrid orbitals that exist, regardless of what type of structure you're looking at. The neat thing is, if you remember what the potential is for an element, I have the names here, the 5 headlining names, these linear, trigonal planar, tetrahedral, trigonal, bipyramidal, and octahedral. From each of these columns, whatever the potential is, that's the number of hybrid orbitals or different types of hybrid orbitals that your compound will have. So whatever the potential is, that's how many letters you'll have. One thing I want you to notice, for the shapes tetrahedral, trigonal planar, and linear, these are for elements that can only have 8 electrons, or that the central atom will only have 8 electrons. Like, for example, carbon, nitrogen, oxygen, and fluorine. Those elements, as a central atom, may only have 8 electrons. There isn't any room to place any extra electrons in the orbitals that they possess, which are only s and p type orbitals. It's not until you get in the rows below the carbon, nitrogen, oxygen, fluorine that we can actually have more than an octet, because now we have some d orbitals that we can place electrons in. So when you look at your trigonal bipyramidal shapes and your octahedral shapes, we can have that because now we have elements that have orbitals that are in the 3rd energy level, or the 3d levels, or just d levels. Okay? So that's how we can get these extra really crazy looking shapes based on, well, we have more orbitals to place electrons in. Okay, so we'll determine the type of hybridization. Once you know the Vesper shape and you have your Lewis structure drawn out correctly, then you may be asked to indicate how many sigma bonds and how many pi bonds. If you can remember this, that a sigma bond possesses 1 sigma, single bond possesses 1 sigma bond, a double bond has a sigma and a pi bond, and a triple bond has a sigma bond and 2 pi bonds, you're in good shape. Normally on the AP exam they'll give you a compound or ask you to draw a compound correctly using the correct Lewis structure, and then with the correct formal charges, and then you indicate how many sigma bonds or how many pi bonds are on this structure. So be sure that you can do that as well. Also, something that's very important that we need to know for determining what type of intermolecular forces we have is whether the compound is polar or not. Polarity has a lot to do with the type of intermolecular forces it has, whether it will dissolve in water or not. Some things to remember about polar compounds. If you have an ionic compound, there are degrees of how well something will dissolve. We haven't talked about that yet, but if you have an ionic compound, we will say that it's polar. Okay? If it's an ionic compound, you have a polar compound. Now, if it's nonmetal with nonmetal, you've got to look at the Lewis structure. If you have a Lewis structure that has the same external atoms all the way around the central atom, and there's no lone pairs, same external atoms, no lone pairs, you have a nonpolar compound. If you have a structure, and again it's a Vesper structure with 1 central atom, if the external atoms are different, okay, you have at least 1 different atom that's an external atom, then you have a polar compound. That's with a single central atom. If you have lone pairs of electrons, a large majority of the time you will have a polar compound. There are 2 exceptions. Anytime that you have a linear shape, okay, or a square planar shape as your molecular geometry for Vesper, you have a nonpolar compound. Any other time that you see lone pairs on your Lewis structure, it will be polar, other than with a linear shape or a square planar shape. Okay? So once you know whether it's a polar or nonpolar type compound, then we'll save that for the types of intermolecular forces. The forces that we're going to talk about next are called intra. Intra has an A, so it's the forces between atoms. And there's 3 types that you need to know for AP Chemistry. First one is ionic. If you have a metal with a nonmetal, no brainer. It's an ionic compound. You have ionic intramolecular forces. If you have a nonmetal with a nonmetal, you have sharing of electrons taking place. You either have equal sharing of electrons or unequal sharing of electrons. And what equal and unequal deal with is the electronegative value for the element. Electronegativity deals with the attraction for other atoms' electrons. So if you look on your periodic table, fluorine has the highest electronegative value. Fluorine wants everybody else's electrons. The element that has the lowest electronegative value is francium, or francium, however you want to pronounce that. because it is the lowest on the table and farthest to the left. Francium is trying to get rid of its electrons. It's begging for elements to take it. So depending on where it's at, whoever has the higher electronegative value has the greater attraction for those shared electrons. So if we have different nonmetals, we have a polar covalent bond. Polar means unequal sharing of electrons, and I think I have that somewhere in here. Unequal sharing of electrons, and it's between two nonmetals. If we have the same kind of nonmetal, then we have equal sharing of electrons. So if you have equal sharing of electrons, there is no quote-unquote tug of war, and I use that tug of war analogy to help you to determine whether or not you have a polar or nonpolar compound. So equal sharing of electrons, nonpolar covalent. Unequal sharing of electrons, polar covalent. And both of those covalents are between nonmetals. Metal with a nonmetal, ionic. And again, that's intra. Intramolecular forces are much stronger than intermolecular forces. So the forces between atoms are much, much stronger than the forces between molecules or compounds. All right, the types of intermolecular forces depends on whether or not the compound's polar or not. If we have a nonpolar compound, you have one choice: London dispersion, or simply dispersion forces. So these are very, very weak. These are actually the weakest of all the forces that exist, including intra, inter. They're the weakest. So that's one reason why we always associate noble gases to have dispersion forces, because again, noble gases have their 8 electrons. They don't form any compounds on a regular basis, or naturally. We have to do some things special to get those to form compounds. And again, they don't ever want to come together and be a liquid if at all possible. We have to actually exert a lot of energy and work to put these things together to make it into a liquid. So even though noble gases are atoms, we have to assign it the very weakest force between the particles. Okay, so again, if you have a nonpolar compound, dispersion forces. If you have a polar compound, now we have 3 choices that we're looking at: either ionic, hydrogen bonding, or dipole-dipole. Well, just like what we talked about with the ionic intramolecular forces, same thing applies to intermolecular forces. Ionic bonding takes place between a metal and a nonmetal. However, this is between compounds. Okay, so make sure you know the difference between intra and inter. So the forces between the compounds is the same name, not the same force. However, if we have nonmetal with nonmetal, and we have a polar we have a polar compound that's nonmetal with a nonmetal. Now we have to determine if it's a dipole-dipole or a hydrogen bonding. Well, hydrogen bonds are stronger versions of dipole-dipole. The difference between hydrogen and dipole-dipole is, well, we have hydrogen atoms in a hydrogen bond, and the hydrogen is actually touching a nitrogen, oxygen, or a fluorine. So again, you can have a compound that has nitrogen and hydrogen in it, but if hydrogen is not physically touching nitrogen, oxygen, or fluorine, you do not have hydrogen bonds between compounds. Now, what I don't want you to do is draw up the Lewis structure and go, oh, there's a hydrogen, there's a nitrogen, and they're sharing electrons. That sharing is the hydrogen bond. That is incorrect. Hydrogen bonds take place between compounds. All right, metallic, we'll never do it with Lewis structures. Just know that if you see a multiple choice type question and you have an alloy of some type, alloys are structures that have different metals or the same kind of metal, metallic bonds. And metallic bonds, honestly, are the strongest of all the forces. I'm sorry, intermolecular forces. All right, the types of solid. Again, metallic solids, so if we have metal or metals, then we have ionic solids. The only thing that we need to care about or worry about when we're drawing Lewis structures is an ionic solid, a molecular solid, or a network covalent solid. So ionic solid, shocking, we have a metal with a nonmetal. Molecular solid, we have at least 2 different kinds of nonmetals. A network solid, we have a single kind of nonmetal. I'm going to go ahead and work out these examples on the next video, so go ahead and check in with me on that.